So welcome to this video on prediction-based exploration. So while in the last video we talked about count-based exploration, we introduced density models and hash function, we will in this video more care about providing an intrinsic reward to the agent through learning dynamics functions, random networks or physical properties. So the first thing, what is prediction-based exploration? So far we actually derived the bonus with respect to the novelty of a state that we have encountered. We said that the bonus correlates with the state visitation, and we encouraged the agent actually to look for states that he did not see that often so far. However, we also could interpret intrinsic motivation more widely in terms of curiosity. What is curiosity? So curiosity says, or is actually the definition of obtaining knowledge from the environment. So what we actually want to have is we want to have an agent that tries to drive to be familiar with the environment dynamics, the reward structure, and things like this. And it turns out that from a psychological point of view, the question is, what happens if we do not use any external reward at all? And we see that when we actually study also humans. So we actually learn without having really a task description or something like this, although we actually also introduce tasks in the setting. However, we see that if an agent only interacts with the environment, actually it learns a set of diverse behaviors. And we also see that it's not just random. So it's actually like playing around and learning about the dynamics of the environment. There's no random, there's not really only a random process involved. And turns out that using the ideas of curiosity within reinforcement learning is an idea that actually dates back until 1991, where actually Jürgen Schmidt-Huber actually already proposed a paper called A Possibility for Implementing Curiosity and Boredom in Model Building Neural Controllers, which is actually really taking the idea of having an agent that tries to learn about the environment and to implement this kind of curiosity into the agents. So what's the basic mathematical idea behind curiosity? And the thing is that what we actually want to have is we want to learn a forward dynamics prediction model. So this is actually what we try to learn if we want to learn more about the environment. And the idea is simple. So we actually have an agent that not only learns the policy, but it also learns a parameterized function f parameterized by theta, such that with using this function we can actually predict, given a certain state and a certain action, a successor state as t plus 1. This is actually also what we have used a little bit in the model-based RL settings. However, this is in this case the dynamics model that we also use in the exploration within the agent to actually create some intrinsic feeling and curiosity. So we actually have also seen that, and I actually pointed out this connection to exploration a little bit in the model-based RL lecture. And what we then do is, so if we actually also learn such a parameterized function f, we want to derive a reward bonus based on the prediction error that we actually have on the dynamics model. So we can actually also define the prediction error of our model. So this should be f index theta. So we actually want to something like a mean squared error on the state. So we want to actually see how bad or actually how good our forward model already is. And depending on the error that we actually have with our forward model, we want to actually provide an intrinsic reward. So if we have a large prediction error with our forward model, we want to actually give the agent a good bonus, because we actually think that we encountered something unusual, unknown, or anything like this, so it's something novel. And if we have a low prediction error, we want to assign a low bonus, because we actually have seen the state very often, so meaning that our model is actually also predicting the next state very well, and this means nothing else than that we have actually seen this coming. So we would have also known that we would end up in this state, meaning that we also have seen this transition a lot in the past. So the idea of using such a forward model just says that our agent uses all the experience sample that he collected so far, and it retrains a prediction model whenever it interacts with the environment. So that's actually the basic idea of using prediction model in exploration. So let's start with a very early idea of implementing such a prediction model in an RL setting, and it was proposed in 2007 by Dyer et al. And it is called intelligent adaptive curiosity, and the idea is the following. So we have a memory M that actually stores all the experiences that we have encountered so far. So experience samples are denoted like this, as we have seen them. And the idea of IAC is the following. IAC incrementally splits so actually have a robotic environment, so we actually have a sensory motor space with different angles and joints and motors. And IAC actually splits the space into certain regions, R0 to N, and it actually starts with like only one region, and it incrementally splits the region into subspaces. And the criterion to actually split such a region is actually that the sum of the variances of two sets weighted by the number of samples that we actually have for that set is minimal. So we actually see in which a certain area of a state space we actually have seen the things, and we actually cut out, or we actually subdivide this region in a way that in the following the two sets actually have a minimal sum of variances. And each of that region actually, for each of that regions, we actually have an associated expert, which is nothing else than a forward dynamics model. And this is trained actually from the data that we actually observe from that region. So this is just the overview of the algorithm, so that we incrementally split things. Whenever we split a region, we actually inherit the full history of all the visitable tuples to the subregions. So this is the actual framework. So we have a classic machine learner M. This is actually the dynamics model, and the job of the dynamics model is just to predict the consequence that actually happens using the context. This is actually the state plus the action. So we actually calculate we actually from that calculate actually difference, because we actually physically realize this action, which actually gives us a real consequence Y. So this would be the successor state, and we calculate the error that actually we get through predicting that. And of course, this error can get us a feedback to our model, because we're incrementally learning also this model. What we then also have is a meta machine learning model, which is actually a model that predicts the error of the dynamics model, and with that prediction, we actually also provide from that prediction. Actually, we assign actually the intrinsic reward to the agent. So the idea is that with each new action, the prediction error of the forward model is actually calculating using the MSE and put into a sliding window associated to that region. And what we actually have is, if we have a decrease in the mean error rate, we give this as a reward to the agent. So this is like the very simple idea of using that. So actually this might also be not a machine learning model in this case. So the actual idea is to have a dynamics model that predicts everything. We have the subregion variant here actually to keep things scalable, and then we can actually use a mean error rate over a sliding window to actually provide an intrinsic reward to the agent. Turns out that high-dimensional state spaces, for high-dimensional state spaces, such a prediction of the images or the next states using the prediction model turns out to become very difficult. And there's an early idea from Stadia, Levine, and Abil that actually uses, or the idea behind this one is actually to train forward dynamics model not in the original sensory motor space, but in some encoding space. So in other words, let's train an autoencoder, like in this case, where we actually, what we actually want to have is we want this autoencoder really to predict the next encoding, so the next state encoding based on the current encoding of the state plus the action. So this is actually what we want to do. This is actually also what we have seen in many other ideas, also in the model-based RL area a lot. What we then can do is we can normalize the prediction error at some time t, by the maximum error we've seen so far. So we actually have seen that that we actually have to weigh things a lot if we care about extrinsic and intrinsic rewards, and then we can actually define the extrinsic reward accordingly. Because in this case, so in this case, C would just be a decay parameter, actually meaning that it's like increasing, and so with increasing time we have a decay, and we actually define the intrinsic reward. This should be the intrinsic reward in this case, and the intrinsic reward is nothing else than the prediction error over some decaying time parameter. So this is actually how we, from the autoencoder, which is actually also trained over time through the iterations again, this actually can be actually trained through the iterations again, and then we can actually define the intrinsic reward accordingly. So actually, sorry, this is in this case. So the autoencoder can be trained upfront using some randomly collected images from the environment, so we can easily obtain them. And then we can actually, or in combination, train them along with the policy and being updated steadily. So, but we also will see a bit also hurdles we have when we actually keep on training autoencoders through exploration strategies of the agent. Okay, and then there was a paper in 2017, which is actually really some guiding work in that area, and this is the intrinsic curiosity module provided by Patak et al. And the idea was actually to have a model that actually early learns how to explore. And what you see in this case is that this is also an experiment that they actually did, that they actually learn how to explore and learn to explore in level 1 of Super Mario Brothers, and then actually they also can explore in level 2. However, they actually learned how to explore and can do that very much faster. And the idea is actually that instead of using an autoencoder like in the previous work, they train a state space encoding of phi of st with a self-supervised inverse dynamics model. And the question is, why do they do that? And the motivation is that predicting some successor state st plus 1 given some state and action pair is not always it's not really like always an easy thing to do, and also not always the best thing to do, because actually many factors are actually in the environment, and many factors cannot be controlled actually by the agent, and they also do not really affect the agent. And there's a popular example that they also make up. Like, imagine this tree with leaves, and like you have your state space is actually changing a lot. So if you model all the trees and how they actually work and the wind, however, if you like really train how an action is actually affecting the state, this is actually not affected. So, and this is also not important to you. Even though you might affect it, it might not really be important for your task. And this is actually something that you do not really want to learn. And this is actually something that currently, if you have the prediction models, your prediction model would just have an error and you would assign an intrinsic reward to it. However, it isn't really connected to the exploration problem at this point. So in other words, such factors should not be a part of the encoded state space, and the agent should also not base its decisions based on these agents. So the solution for this is we learn an inverse dynamics model G. So the inverse dynamics model is formulated like this. It is a function that takes as an input the encoded state, the encoding of the state st, and the encoding of the state st plus 1, and it should predict the action that actually is being necessary to take in order to come from state st to state st plus 1. And if you train a model like this in combination with your state space encoding, the feature space will only capture those changes in the environment. So this the features that actually been using for that. The feature space will only capture those changes in the environment that are really related to the actions that the agent takes, and will ignore the rest. So maybe look a little bit, so one step deeper into the intrinsic curiosity module. So from a more formal point of view, what's given? So actually we have a format model f that is parameterized through some parameters theta f. We have an inverse dynamics model as we introduced right now, which is called G, which is parameterized by parameters phi, so inverse dynamics. And we have an observation as usually st, at, st plus 1. from what we've also seen is we want to predict actions actually through our inverse dynamics model. So we want to have a state encoding of st and st+1 as an input using a parameter set of theta y. We actually want to predict the action that leads from st to st+1. So this is this kind. So this is this one. What we also want is a forward prediction model, and the forward prediction model should actually produce the state encoding of st+1 as a function of the state encoding of st and the action that is being taken, and it is parameterized by some parameter vector theta f. And then the intrinsic reward that we actually want to assign to the agent as a bonus is some function over, it's just like how well is our forward model actually predicting the successor state. Like this is the mean squared error over the prediction model and the real observed successor state encoded through our encoder. And this is actually how all of the things play together. So we have we actually an initial state. So you actually have to read from the left side. You're actually coming from state st. You just sample your policy. Your policy gives you an action A, and together st and at, your intrinsic curiosity model will actually your forward model could actually produce the state st+1. However, what you also do is you actually take the action in the environment, giving you a real state st+1, and then you go over again. And if you now zoom in what's happening in the intrinsic curiosity module, so the inputs is st, at, and st+1, and the output should be the intrinsic reward. So you see it here again. So you have action at, st, and st+1, and here's the reward. And what you actually train is you have actually your forward model, which is nothing else than your state input compressed through your parameterized encoder in here, and your action at plus your encoded state st together should actually predict the encoding of the successor state. So you actually observe the successor state. From the successor state, you also use the same features. This is actually shared. You actually compute the feature representation of st+1, and through these two, this is real observations in this case, you actually train an inverse model that's predicting the action that needs to be taken by the agent to come from here to there, which is also something that might be different from what happened in reality. And based on the forward prediction model error in here, so the mean squared error in here, you can actually calculate the intrinsic reward. So the question is, how can we actually optimize for such a thing? And the answer is like simple in this case. So we just optimize the policy jointly as a whole. So we actually want to minimize. We find a set of parameters that actually minimize the following combined loss function. So what you see in here is like a weighted loss function. So you have beta in here and lambda in here, which is just a weighting over the policy gradient loss. So this is the usual policy gradient loss for our agent. You see here, this is actually the loss of the inverse model, which could be this is actually this loss here combining these two actions. This could be for continuous action, it could be just the mean squared error. For continuous basis, you could just use a softmax, maximum likelihood under a multinomial distribution or something. And then in here you have the error of your forward model, which is also the mean squared error over the prediction over the encode representation of your so it's the encode representation over your state encoding. So, and as you actually learn both of them, you will actually, with time, you train a set of features that actually describes very well how to encode your important and relevant things to the states, because you actually try to optimize for the inverse model to get the same actions. This actually requires that the feature set here is complete. And this combined and joint optimization actually leads to the fact that you actually extract the correct number or the correct features from the environment. That's actually important for your decision-making process. So actually they proved it in that paper using some, I think it was with Doom, so a rooms environment in Doom. However, they also followed up with a large-scale study on the environment. And what they actually did is they trained the ICM module, and they altered many parameters and run them on the Atari suite. And what they actually wanted to know is actually, they wanted to know how is the curiosity, so we actually want to analyze the influence of curiosity by purely using the intrinsic reward. So in this case, they wanted to just know is, if we provide to the agent just the intrinsic reward defined by this, what is happening? And the next question is, what requirements must theta, so the features that we actually have, satisfy? And when does it actually work best? And they make actually a theoretical work on this. They said that a model that actually encodes the state space, it should be compact, sufficient, and stable. So it must be a compact representation. So our state space is not high dimensional anymore. It needs to be sufficient. So everything that is really needed for the agent to solve the environment should be in there. Because actually, if it's not in there, you cannot control it. And if you cannot control it, you cannot learn it. And it should also be stable, so it should not really, like with new samples from the environment or new areas from the environment that gives us new information. It should not change the representation of states that I have been visited before, where my policy actually builds its controls on. And they actually evaluated a few well-known or successful models on that. The first one is a VAE, so it's a variational autoencoder. The second one is the inverse dynamic features. The third one is random features and pixels. I will give you in a minute what this is. So variational autoencoder is like the idea of an autoencoder that has in the latent representation. So it actually models the data through a set of Gaussian distributions. Inverse dynamic features is what the originally ICM module is actually proposing. Random features is just a randomly initialized convolutional neural network, and they just put this in, to put the image in, and use the representation that actually comes in before the softmax layer, that use that one as a representation of the image and the raw pixels. And it seems that if I just keep on training on my if I just see more information and retrain my model, the inverse dynamics features both and the VAE, they will actually be non-stable. So where they will actually, if I retrain the model and keep on training along with the policy, we will actually see also that our encodings of previous visited state will also change through time. So it's not stable. Random features on this sense, actually, because I actually have a randomly initialized neural CNN and this is fixed, then they will just be fixed. And if I just use the pixels, yeah, it's like high dimensional and maybe not working. So it might be stable, might be also not be stable. About compactness, actually, VAE and IDF, they can be really compact. So there's like work that uses very only like between under 10 latent representation vectors to actually work with VAEs and IDFs. So they can be really compact in a sense. For random features, there might be a compact representation, or there might also be some non-compact representation. And pixels, of course, is not compact. So in terms of sufficiency, so in principle, the VAE could be sufficient in a sense. From the IDF, we just don't know it. From the random features, we also don't know it. And from the pixels, of course, they are sufficient because we assume that the state space is complete, so they would be sufficient. So what they then did is they ran a large-scale study and ran a lot of experiments. So as a baseline algorithm, they used PPO. They normalized reward advantage in observations in this case. They had 128 parallel actors, they normalized the features, and they had an infinite horizon, so they avoid the done flag in the exploration. There's it's a non-episodic setting in this case. And this is actually the results. And you have you have like the hard exploration games in here, like Montezuma's Revenge, and also the not so hard games such as Pong. And you can also draw some conclusions from it. So the first thing that you actually see is that the random CNN features, they actually perform surprisingly strong. So the random CNN feature, so we would actually expect that the inverse dynamics features, so the yellow ones, is actually capturing all that there is need to know from the environment. And while the yellow curve almost every time like outperforms pixels and VAE features, it is really like something like on par to the random CNN features. However, what the authors also found out is that the inverse dynamic features actually generalize better through certain rooms in environments. So like if you have Super Mario Brothers and you apply the inverse dynamics features in level 1, you can really outperform everything in level 2. So there's in the paper you find an experiment on that where you can actually see that you learn to explore in level 1 and then you can really like explore fast in level 2. And then there was also in this paper, actually what I also told you in the beginning of this lecture series, they introduced the concept of the noisy TV example. And they have seen, so the noisy TV was the thing that we had this image or the TV in the environment that has some, there's a like a really random process, an unpredictable random process in the environment that actually provides information to the agent that it cannot learn. And what they have seen is that the noisy TV actually drastically slows down the learning as the extrinsic rewards are considerably lower in time. So if you see this, so you see only the extrinsic rewards, something like the reward process, so they like the performance of the agent, and you see that also using the curiosity module in the curiosity-driven learning. If you have the TV on, which is actually the lower two curves, you will see the extrinsic reward that actually the agent is actually getting. And you will see that the extrinsic reward is like really low, meaning that it doesn't really work well in the environment. However, if the TV is off, it really works well. So it actually really gets a high reward from the environment, and meaning that it really gets stick to the noisy TV as it tries to predict what's happening there. And so this is actually the stochasticity. We can actually put that down to the stochasticity in the environment, and the stochasticity really poses problems to the setting. However, stochasticity is not always a problem in general, because sometimes the agent can also escape from that. Okay, so this is actually an idea to use forward dynamics and to learn the forward dynamics. However, there's also another kind of algorithms that actually use the concept or class of exploration that are actually based on information gain. And this is actually one of these algorithms is actually VIME, so variation and information maximization exploration. And before we actually introduce VIME and how VIME is working, let's do some useful theoretical quantities first, because it's actually talking about information maximization. So just to give you some background, so P of x is usually describing a distribution, maybe over some observations x. H of P of x is actually the entropy, so describing how broad our experience samples P of x actually are. We have pi of s, something like a policy in this case, would be something like a state marginal distribution over policy pi. We have the entropy over policy pi, which would be the state marginal entropy of policy pi, meaning something like quantifying the coverage of the policy. And we also can define mutual information. In this case, so the mutual information of a state as t plus 1 and an action at is nothing else than the state marginal, the entropy that has been in place before minus the entropy that I have afterwards, which is actually something like we can call the empowerment of some new information. And so as y belongs to a class of exploration based on information gain, and when we actually want to use information gain, or we want to reason, if we want to reason about information gain, the question is, what we actually want to have is we want to select an action that will result in an observation that in expectation will give the most information on some variable of interest, which could be the policy. So information, and then before we want to do is, so information gain, and the question is information gain about what? We could actually define the information gain over a reward function. However, optimizing the information gain over reward function makes no sense, maybe, as we have seen that the reward function is actually almost zero everywhere in the settings that we're currently looking into. We could also describe the information gain or optimize the information gain over the state density. So this sounds a little bit weird, but it would make sense actually, because we want the state density to be changing, and this can also be interesting in something. It could also be interpreted as something like an information gain. However, what we actually want to do is we want to actually optimize the information gain, maximize the information gain over the dynamics function. So this actually makes the most sense, as we want to see something novel, and this is actually what we want to do. What you will see also in the upcoming slide, and actually why there's most of the theories kicking in practice, the exact information gain is something that's intractable to compute in practice. So regardless of what you're estimating, so the information gain is something intractable to compute. Hence, we need to approximate it, and you will see that in a minute. Maybe let's introduce the idea of the algorithm Wine, which is actually taking care a little bit about it. So the idea of Wine is, given an environment transition function P and a forward prediction model small p. So this is like usually what we do. The forward prediction model P is defined over some parameters theta, and theta is part of a parameter that bar theta in here. And what we see is we see trajectories of this form. So this is CT, meaning that everything that happens from a state S1 to a state ST. And what we actually want to do from an information theoretic point of view, we want to reduce the entropy whenever we acquire a new knowledge. So we actually, whenever we see new state, we want to actually reduce the entropy most as we can, which in other words means that we want to maximize this term here. So we want to maximize the entropy from before, and the entropy after seeing ST and AT plus the history that we have seen before. So this is actually what we want to maximize. So if we want to reduce entropy, we want to maximize this term. And as we do this in expectation, we can also see it so but we can actually, this actually boils down to the Chi-L divergence of the two distributions, meaning that we want to maximize the Chi-L divergence between the parameters from before having so the parameterized prediction model that actually has been optimized for our trajectory CT to the parameterized policy that has been optimized through CT plus the newly observed transition. So this is actually what we want to maximize. And the question is actually how to do this. And we see this in the following. So this is like very theoretical. If you are not getting really along with it, it's not that bad. So if you're like interested, you can also look into some papers that actually introduce variation and inference. So the paper on variation and autoencoders also give you a little bit hint on that. So I think on the high level, I think the idea will become clear anyway. So the problem is, if we want to estimate the Chi-L divergence of this term and we want to maximize, the problem that we usually have in this setting is that these posterior distribution, in a sense, it is not it is intractable. So if we want to compute these posterior distribution in here, you can reformulate everything like this using Bayes' rule. As the action does not affect the belief, it goes out, and you will end up in this term, in this case, in this term, and you will see that these terms, they are really hard to compute directly. And what you usually do in work on variation inference, as it is very difficult to compute the posterior distribution here,
So as it's difficult to compute the probability of theta under your trajectory ct, we want to approximate it with an alternative distribution. We call this alternative distribution q phi of theta. And what you usually do is you do this with a variational inference. So actually you use the formulation of the variational lower bound, meaning that you want to maximize distribution, which is equivalent to maximizing p of ct under the parameters theta and minimizing the KL divergence of these two terms. So this is actually, this boils down to exactly this kind of things, and this is actually something that you really can do in practice. And if you really maximize this term and minimize this term, so you actually want to maximize the probability of ct under theta and minimize the KL divergence between these two things, you can actually use this approximated distribution that you can use, that you can have using a trained model, and you can actually define the intrinsic reward that you provide to the agent as the KL divergence of the old and the new parameters. So in other words, phi t plus 1 are the parameters of q after seeing at and st plus 1. So this is actually after we have been taken the step in the environment and getting this new relief and actually taking it into account. If you define the intrinsic reward like this, be careful, because you actually need to normalize by division and a moving median, for instance, about over your past KL divergences if you use this for reward. So in VIME, actually what they do is they use a Bayesian neural network which maintains a distribution over the weights. So they model the weights as independent Gaussians, and they can then sample a set of theta from this independent Gaussians, and then they can actually, through this process, they can actually calculate the KL divergence. And what they do is, in this case, they estimate the KL divergence using a second order Taylor expansion using the Fisher information matrix. Sounds hard, as we have seen in TRPO, however, it's easy because we have a diagonal matrix in here. So they actually have a Bayesian neural network from which they can sample the parameters, and the sampling allows to calculate the KL divergence, which can then be used as an intrinsic reward that can be given to the agent. Okay, so this was a really like an information theoretic point of view to actually also address this issue. We will now go a little bit again into the prediction model and into the neural network architecture thing. Another way to actually to stabilize the training if you want to use a prediction model, is actually to use more than one prediction model. So actually the idea of self-supervised exploration via disagreement is to use an ensemble of prediction model and use their disagreement as a bonus. So this is also something that you can do. So you could also do this curiosity-driven exploration. You can do the variational maximization, so VIME, and you can use an ensemble of prediction model and use their disagreement as a bonus. And this work actually proposes this. So you have simple prediction models in here, and you have an ensemble of them. So in the paper, I think they use 5. They use random features as an encoding, and all these prediction models actually provide a prediction of the next state, and you actually want to actually minimize this term. So you actually have, and what you then do is you provide So if you have a high disagreement, you have a low confidence in your prediction, meaning that you need to do more exploration. And the nice thing about this work is actually that the intrinsic reward that is being provided through the ensemble is actually fully differentiable into your prediction model. And this means is actually that the intrinsic reward actually can be directly optimized. In other words, this means that from the differentiable intrinsic rewards, the policy agent can actually directly infer how to change its action in order to prioritize the exploration process. Because you actually get from the prediction model a differentiable equation, the policy can actually select an action that helps the ensemble to be more confident in its prediction. And this actually makes it very efficient because it's actually differentiable through the model, and you can use this gradient signal to actually incentivize exploration. Okay, so
these are actually the kind of ways how you can use prediction models to actually guide exploration. However, we have still the problem. So we have still the problem with the noisy TV. And in the noisy TV example, or if we study the noisy TV example more closely, we can identify certain sources of prediction errors. And the thing is, the prediction error is high in actually 3 cases. The first one is, it is high when the predictor fails actually to generalize from previously seen examples. So novel experiences then correspond to a high prediction error. The second one is actually because the prediction target might be stochastic. So if we have a stochastic prediction target, our prediction model cannot really predict it. And the third reason is because the information necessary for the prediction is missing, or the model class of predictors is too limited to fit the complexity of the target function. Meaning that if our forward model is not complex enough to capture the dynamics of the world, it will also have a prediction error. And this is something that could also be really critical in practice, because the class of algorithms and their complexity is not really known, and it should not be too large, because then I cannot really learn it. And if it's too low, I will always have a large prediction error. While 2 and 3 are the problematic thing, 1 is actually what we wanted to have. So we only actually want to have a high prediction error if it cannot generalize to previously unseen examples, seen examples, and this is actually what we really want to have. However, we do not want to have 2 and 3. So actually the thing is, how can we avoid the issues that are raised by 2 and 3 using the prediction model we introduced so far? And the question is, or the idea is, what if the focus of our prediction task is not on the environment dynamics at all? So why are we talking about environment dynamics? Wouldn't it be easier to focus on something else? And the idea is, don't care about the dynamics. Sounds crazy? Just wait. This is actually the idea of random networks. So there's actually, I would actually tell you 2 algorithms that are actually part of this class. So the first one is DORA, so Directed Outreaching Reinforcement Action Selection. And the idea of DORA is the following. So we assume that our world consists of MDPs, of course. So and DORA actually makes use of 2 MDPs. It just takes the original MDP, and a second MDP is actually a copy of the original MDP. However, the reward at all of the states is 0. So there's no reward process. So the reward is just overridden. And what now is being learned is actually what DORA is actually doing is actually DORA learns the Q function on the second, and uses this Q function and calls this E value, so error values. So what DORA is actually learning is, it's learning a function called ESA. And in the beginning, the E values are actually initialized with 1s. And the goal of the model is actually to predict all the E values to be 0. And if we define it like this, we can simply say that state action pairs that have a high E value that lack information. And this idea is very similar to visit counters. We have the pseudocode in a minute, so then we actually see a little bit more closely what's happening here. However, if we just learn the E function, actually we can use the predicted E value as an exploration bonus in this kind of sense. So the larger E is, the larger that E, this is actually the logarithm in here. So the larger E is, the higher is the bonus in this case. So let's take a look at the pseudocode at this point. So it starts like this. So we have some stochastic action selection rule F, we have a learning rate alpha, and we have an exploration discount factor. What we do in the beginning is we initialize our Q function with 0s and our E function with 1s. And then we just follow up and go on like this. So while not being terminated, we just choose an action A, which is actually the argmax over some selection function. Let's just don't care so much about it right now. Then we observe transitions, and with these transitions we do the following. We do something like a similar Q-learning update in here. So this is just very similar to what we usually do. However, we just also make a Pauliac over the learning rate.
in this case. However, we do the same with the E function. So with the E function, we do something similar to the Q function, and what actually follows from this iterative update rule is, at some point where we actually selected a state action pair often enough, this will be coming close to 0. So the knowledge in terms of interpreting the MDP in this case is that we will have an initially selected E function table that's actually implemented with once, and it will slowly decrease to 0. And if it's like 0 everywhere or close to 0 everywhere, we actually have seen all the states enough times, or we have deduced enough information from the states enough times, and we can then also follow then that our Q function is stable. What we can do from it, while this is like defined in the setting for a tabular setting, you can also use this in something like a DQN-based framework, where you actually approximate Q and E both at the same time. So you can actually use this as something like a state visitation counter in this Markovian setting. Okay, one more thing about it, a very well-known technique called random network distillation, and it follows a very similar idea than DORA. However, it takes it to the next level. So the idea of random networks is very similar. The thing is, we want to predict something that is independent of the main task. And what's the idea of R&D? So R&D actually uses two neural networks. So it first uses a randomly initialized but fixed neural network that just transforms a state into a feature space. We have seen this in the random feature setting from the curiosity module. However, what we then use is we train a second neural network, and this second neural network should not really predict forward dynamics. However, it is just trained, so it's like a copy of the fixed network. So it has the same architecture, so it's principally capable of approximating the same function. And this network is actually trained to predict the same encoding, so the same feature encoding of the states as the fixed network. So to give you a little bit of intuition about this one, so this was the next state prediction module that we have seen a lot in the forward prediction model. So with an action A, we have the environment, we get a representation of the environment, so some image on which we calculate features. And we also have a predictor that uses the old state and uses the action to give you some prediction, and we take a mean squared error to actually calculate our intrinsic reward on it. Of course, we also take all the information to just backpropagate and optimize. In the R&D setting, it's different. So actually we have an action, and the environment provides us a new observation. And with this new observation, we actually take the randomly but fixed network to calculate a feature representation, and our predictor is actually trained to predict the same thing. So it's actually the job of the network is actually to predict the same features as the other network, and the reward is just the difference between those two feature encoders. And by this fact, we do not really need to learn. So actually, what we want is that both networks actually predict the same things, and this means that we do not really predict environment dynamics. So we want to have the predictor to predict the same thing as the feature encoder that has been fixed from the beginning. So that's actually what we want to do. And the intuition behind this is that similar states have similar features. And if we have already seen them, if we have already seen those features, our predictor model should also produce the same features as the feature model, because it actually has seen it once and trained on it once. So actually, with seeing more and more states, the predictor will actually, with time and having seen and trained on it oftentimes, will actually produce the same feature representation. This is something like predicting the features, but not predicting the dynamics. And we can use actually the mean squared error between those two predictions as an exploration bonus. So this is the idea behind R&D. I think it's very, very simple but it throws away the problem of really learning the environment dynamics, which can be really complicated in practice. So what is the advantages of such a synthetic prediction problem? So the fixed network actually makes the prediction target deterministic. So we do not have stochasticity in the environment that we need to care about. So we have such a feature representation of a state, and we learn another model that actually is trained to also predict the feature representation of the state. So this actually bypasses the issue that we initially introduced, so the second issue. And the next thing is, as the predictor and the target network are actually using the same network architecture, so the class of functions that the predictor needs to learn and needs to represent is actually the same class of functions that can be represented by the target network, meaning that we do not have the issue that our network complexity is too large or too low. So this actually bypasses the third issue that we want to do. And the first issue actually was that novelty should have large prediction error, which is actually what we want to maintain. And this is actually also maintained in here. Okay, so actually, what are the results from the R&D paper? So R&D works really well on hard exploration games. So this is like a really nice visualization of OpenAI that you can see in this blog post, where you see actually what rooms R&D discovers in Montezuma's Revenge. And it actually, if you maximize the R&D bonus, you will actually find half of the room in Montezuma's Revenge. However, just one side or two side notes in this case, normalization is very important, so the scale of the rewards is tricky to adjust given a random network as a prediction target. So this is like a little bit tricky. What they did in the paper is they normalized the reward by a running estimate of the standard deviations of the intrinsic return. So this is something that you usually did a lot, like maintain like a window and you average the last ones and provide this as an intrinsic return. And what they also found out is, and also what the others did in the curiosity paper is, non-episodic settings in principle work better because in cases without extrinsic rewards, because then the return is not truncated at the game over and the intrinsic return can spread across multiple episodes. This is also what have been pointed out by Partag and Burda et al., but was not really explained that well. However, Burda et al. Actually also tried to do a little explanation on them. So what they did is, so in their experiments, they saw that treating the problem as non-episodic resulted in a better exploration because then the setting of the return is not truncated at the game over. Here you see some motivation that actually explains it a little bit. I will not read it out loud at this point. But what they also said is, however, using non-episodic returns for extrinsic rewards could be exploited by a strategy that finds a reward close to the beginning of the game and then deliberately restarts the game by getting a game over and repeats this in an endless cycle. So, like for the intrinsic reward, it would be good to have no truncated rewards, so having a non-episodic setting. While for the extrinsic rewards, this could be really problematic because then you can come in such an exploitation strategy. So this was it for the prediction-based exploration. There is one more thing to mention that really lies a little bit aside from what we have discussed so far, but it might be a really interesting research direction and practice. And this is a paper of Daniel et al., where they actually trained an agent that learns to perform physics experiments. And the idea is very, very good because in many applications, actually, it would help if the RL agent would explicitly understand some things explicitly, such as the mass of the friction of some things. So if we could explicitly model such elements in our MDP, this would really help and benefit. This would really help the RL agent that can actually benefit from it. And what they actually did is they let an RL agent actually learn such properties. And what they did is they have two phases. The first one is an exploration phase where the agent actually interacts with the environment without any specific task. It just can interact. And at the end of this exploration phase, they just ask a question.
maybe which of the boxes in here is the heaviest, and they just give a reward based on some labeling action, some, like in this case blue, and based on this kind of setting, the agent must efficiently play around in order to figure out the physics and provide a correct answer in the end. So in a sense, exploration happens implicitly. So in this case, they demonstrated with two different environments. The first one is the boxes in here, where the question is actually which of the boxes is heaviest, and they have different configurations of how colors and masses are actually assigned, and only through this labeling action it performs like experiments in order to figure out in the simulator like something like a notion of mass. They also have a little more complicated example in here. I think it is called a tower example. So so the job is actually to answer the question how many rigid structures are in that environment, and in this case the tower is composed of 5 blocks, but could decompose actually in different rigid objects in many different ways. And what you see on the right side is actually over the training sequences, or actually how the time steps of exploration, how well the agent can actually answer the question of how many rigid objects are in the environment. And he has really to play around and really infer such physical properties from the environment.